If you recall, yesterday, we looked at a couple of line integrals where we integrated a vector field along two different paths, but those two different paths had the same starting and ending points. And then we got the same value. The reason that we got the same value was because secretly the vector field that you were given was a gradient field. And so the fundamental theorem of calculus applied. So the fundamental theorem of calculus for line integrals says that the integral along any piecewise smooth oriented path from P to Q of a gradient dot dr is just the potential function evaluated at the endpoints, f at q minus f at p. The same way we integrate from a to b f prime of x with the fundamental theorem of calculus, f at b minus f at a. So this any piecewise smooth oriented path from P to Q tells us that gradient fields are path independent. The other word for that is conservative. So gradient fields are conservative. Lots of terminology for things, but this is a math class, so you should expect a lot of terminology for things. So we could have greatly simplified those two problems that we did yesterday. We didn't have to parameterize the curves. If we had noticed that we had a gradient field, and if before the problems I had told you about the fundamental theorem of calculus for line integrals, we could have avoided a lot of work by identifying the potential function and then just evaluating at the endpoints. So let's do that here with a seemingly complicated looking potential function. I wanted it to be long enough that it looks messy, especially if we consider the prospect of plugging in x and y's and then integrating. That seems like it might be messy. And then C is at least it'd be simple to parameterize the curve. But we don't have to. What we want to do is we're going to check if f is a gradient field. So let's check if this vector field is path independent. And then we can apply the fundamental theorem of calculus and we'll be well on our way. So we're going to ask ourselves, before we parameterize the curve and calculate the line integral. So this is the thinking before we go through the trouble of parameterizing C and finding dr and all that, let's check if f is path independent. Because if f is path independent, then we can just find the potential function and evaluate at the endpoints 1, 2, and 3, 18. And what we notice is that in both cases, if we integrate sine of xy, dx and dy, note that the y is the derivative of the inside with respect to x, and x is the derivative of xy with respect to y. So we'll notice that f is the gradient of the function. So f is the gradient of f So if we integrate sine of something, we should have negative cosine of something. So f of xy looks like it's going to be minus cosine of xy. The derivative of negative cosine is positive sine. Then we multiply by the derivative of the inside. So fx at xy is derivative of cosine is negative sine times the derivative of the inside. Derivative of xy with respect to x is y. And fy, the derivative of negative cosine is positive sine times the derivative of the inside with respect to y, which is x. This is the other reason that I picked this function, because it would be easy for me to integrate before I have been sufficiently caffeinated. So if we want to calculate the line integral along C of f dot dr, we can just evaluate the gradient of f. Sorry, we can just evaluate the potential function at the endpoints. We went from 1, 2 to 318. So we'll take f at 318 minus f at 1, 2. So we'll have minus cosine of 3 times 18 minus negative cosine of 1 times 2. So looks like cosine of 2 minus cosine of 30/24. It would have been great if I had worked this out, if I had picked an example that would work out to -4, because then I could start this belief that it's just always going to be -4. -4 was actually the number of the day yesterday because I was working on the Fundamental Theorem of Calculus in Calc 1, and the one that I picked worked out to -4. All right. So, and a good exercise at this point, that I think what most of us would do is say, great, this was a gradient field, path independent, so we can just evaluate the potential function at the endpoints. Let's move on to the next one. But you can probably guess what I'm going to say next. A good exercise, since we're new at this, would be to parameterize the curve C, drop it into find dr, evaluate the vector field at the potential function, and then work out the line integral to see if it comes out to cosine of 2 minus cosine of 54. So now I would recommend that you check that this result agrees with just the whole process. So to get you started on that process, I don't want to do that whole thing today. I kind of do because it's a nice smooth thing, but it's better to leave it as an exercise to the reader. Notice that we're parameterizing this parabola y equals 2x squared. When you're parameterizing a function, the easiest way to do that, since y is a function of x, just make x the parameter. So if you want to parameterize c, just make x of t equal to t and y of t equal to 2t squared. And then since x of t is t, t will go from 1 to 3. So it's easy to parameterize a curve when your curve is a function. It can be written y is a function of x or x is a function of y. So for fx, the derivative of cosine of something is negative sine of that thing. So the derivative of negative cosine xy is positive sine of xy times the derivative of xy with respect to x. The derivative of xy with respect to x is y, because y is the constant and x is the variable. And then just switch it up for fy. The other question would be, how do we get minus cosine of xy? And that's because I picked a function that I knew would be easy for me to integrate right away. Because I saw the sine of xy in both cases, and I knew that this y represented the derivative of the inside with respect to x, and the x represents the derivative of the inside with respect to y. It allows us to make some complicated appearing functions, but they have some really strong similarities. So going after the potential function wasn't too difficult. Any other questions? Just on that note, it's a bit mechanical, but on that note, let's suppose that we have a vector field f, and it's going to look complicated. We're going to have 2xy squared z e to the x squared y squared z times I. At this point, you could probably see what the next term I'm going to write is. Take a minute and think about, not a whole minute. See if you see it right away. Might be more clear now. So the next one is going to be plus x squared y squared e to the x squared y squared z times k. What you want to notice is that we've got this e to the x squared y squared z. That's in common with all of our components. And the stuff out in front is just the derivative of the inside with respect to x, the derivative of the inside with respect to y, and the derivative of the inside with respect to z. So we could think of this as just, we could think of doing a substitution. In integration, if we don't see it right away, the first thing we should think of is substitution anyway. And so if we set w as x squared, y squared, z, instead of writing dw, because w is a function of 3 variables, I should write dw dx, dw dy, and dw dz, they'll all be partial derivatives. So I could also just use the subscript style. The derivative of w with respect to x is going to be 2x, and y squared and z are constants. The derivative of w with respect to y is going to be 2y times x squared times z, since x squared and z are constant with respect to y. And finally, wz is just going to be x squared. The derivative of z with respect to z is 1. So we'll just get x squared, y squared, since x squared and y squared are constant with respect to z. So now we can see our gradient function, or f is the gradient of f, where our potential function looks like it's just going to be e to the x squared, y squared, z. So if this, we wanted to find a line integral of some smooth, piecewise smooth oriented path through this vector field, we would just have to evaluate this potential function at the endpoints of the path. We're not ignoring what's in front. What's in front is where we're, that's all going to be the dw. We're thinking of integrating 2xy squared z e to the x squared y squared z with respect to x. So if we think about, think about the integral of 2xy squared z e to the x squared y squared z. I'm just going to use our old school notation. We're thinking of doing this. And if we look at only what matters here, with respect to x, y squared and z are constant. And we notice that this y squared z, this is all constant. And I have the same constant up here, which is what making this work. So we're not ignoring what's going on out in front. We're making sure that that fits. But with respect to x, these are just constants. And more importantly, they're the same constant. So we're thinking of integrating. This problem looks like 2 times some constant, k, x, times e to the k times x squared. Because the y squared z, that's all just constant stuff. If you don't like the constant k, pick a constant. So this is like 2 times 5 x e to the 5x squared. And we're just integrating this with respect to x. So we're doing a substitution. So we said w is the inside 5x squared. So dw is 10x dx. And so this works out to the integral, this just works out to e to the 5x squared. Because the 10x dx, that was all the dw. And we're just making sure that we're going to get the same integral when we integrate the component of the I component with respect to x, and then the j component with respect to y, and the k component with respect to z. So we'll also have to look at the integral of 2x squared yz e to the x squared y squared z dy. And then we can make the same observation. X squared z is all constant. And so this integral really just looks like the integral of 2 times some constant. Oh, I shouldn't use k. 2 times some constant times y e to the constant times y squared. M is just x squared z, which is all constant with respect to y. dy. We're just doing our old partial derivative thing. That's the derivative with respect to y. So x and z are just constants. And then so we end up in our eternal algebra struggle, where all we do is use numbers, and then algebra comes along and we say these letters represent variables. And then we also say in algebra, sometimes these letters represent constants, like y equals mx plus b. And then in calculus, we start doing partial derivatives, and we're like, oh, no, no, no. X, y, and z, those are all variables. See, all variables. Oh, except when we're ignoring the fact that y and z are variables because we're integrating with respect to x, we're going to treat them like constants. And then at that point, the algebra student in you is looking at me and it's like, oh, you lied to us. And then we're like, oh, no, no, no. What we said was true from a certain point of view. So we've noticed that this vector field f is path independent because it's the gradient of some potential function, specifically e to the x squared y squared z. So let's suppose that we wanted to calculate the line integral and see yeah, I'm just actually going to use this one. It's funny that way. If I can find it again. So C is a circle of radius 1 in the plane z equals 1, centered on the z-axis, at this point, you should be, since we know that we're dealing with a gradient field, you should be thinking, dude, just get to the end points. So centered on the z-axis, starting at 1, 0, 1. And you're like, oh, finally, a starting point. and going once around counterclockwise. So our starting point, 1, 0, 1, that would be the point P in our fundamental theorem, which we know we get to use because we have previously entered F in evidence. F is a gradient field. And so this is our starting point, P, and we're going once around the circle counterclockwise. And so that is also our ending point, Q. So what is the line integral along this curve of this gradient function dot dr? Starting at P, P is 1, 0, 1. We're starting at 1, 0, 1. We're going around the circle and ending at 1, 0, 1. F is a gradient field. What's the line integral of this gradient field dot dr along this curve? Since we're starting and ending at the same place, we don't even have to bother evaluating the function because we're evaluating the function at the same point and then subtracting the same number. So we'll end up with 0. This is because the curve that I described here is what we'll call a closed curve. The starting and the ending points are at the same place. C is a closed curve. Any questions? All right. What we really want to get out of this is, or what we want to focus on from today is less about finding these potential functions, because that's just going to be a question of integration, weirdo partial derivative style integration, but it's still just a question of integration. I want you to focus on the big picture and seeing the similarity between the see how we can call both of these things the fundamental theorem of calculus. And they both have the same kind of stuff going on. We're evaluating some kind of derivative, either just a derivative or a gradient, which is made up of derivatives, along a one-dimensional curve, either a one-dimensional interval from A to B, or some one-dimensional curve C in R2 or R3 or Rn. So the fundamental theorem of calculus for simple integrals says evaluate an antiderivative at the endpoints of the interval. And for line integrals, evaluate the potential function at the endpoints of the curve. We only get to do this if we're integrating a gradient field, if our vector field is a gradient field, which means it's path independent. The other thing to note that is that if a vector field is path independent, then it is a gradient field. All right. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.